Hey, welcome back. Uh, so in this lecture, we are going to continue discussion about a binary search tree. Okay. So for this lecture, we are going to discuss the operations in binary search tree. So we start with search operation. So how we conduct a search in binary search tree. So here is the algorithm pseudocode for the search. We try to search some item in the tree to see if it exists. Okay. And so you're going to compare the item with the data in the node. So if you find it, then definitely return true. Okay. If the item is less than the data in the node, then you go to left. Otherwise, you go to right. Okay. If you reach a null node, then you return false. Okay. So that means the item does not exist in the tree. So let's take a look. First, let's see how do we find 59. Okay. So we start at the root node 55 and you compare 59 with 55. So it's greater than 55. So we are going to follow its right child. Okay. The right child is 65. Okay. So then you compare with 65 and we can find it's less than. So then we go to follow its left child. So we come to 57. So then 59 compared with 57, it's greater than. So you follow the right subtree, is it the right node? And then you reach the right child and then compare with the item, okay? And we can find it's equal, is it? So we find it, and then here we return true. Okay, so you can find it. Okay, so next let's take a look with 31. Okay, so 31 compare with 55, so it's less. So we should go to left child. Then we reach 50. So then 31 compared with 50, it is less than. So we should go to its left child. Okay, left child is 38. So then you compare with 38, it's less than. So you go to its left. Its left is a null node. That's it. And here it says if you reach a null node, then return false. That means 31 does not exist in this binary search tree. So that's how we conduct a search. Okay, then let's take a look how we insert a new item, okay, to a binary search tree. So insert operation. So here is the pseudocode, the algorithm. Okay, so same thing. So that's why we see the root node is important. We always start at root node. That search we already see start at root node here. Insert we also need to start at the root node. Then you move along the tree, okay? And of course, you also need to, because you're going to do insert, so we need to keep track of the parent node and the node, the current node. So there is a parent node and the current node, maybe we can call it a cursor, is it? Yeah. And move along the tree, okay? And if the item is already in the tree, then definitely you cannot do inserts because binary search tree is a unique item. So no duplicates is allowed, okay? And if reach a null node, then stop, then insert as a child of the parent and return true, okay? Otherwise, you just do search. So basically for insert, it does the search for for half of the operation. As you first need to find where to insert. So that's a search. Okay. So after you find the right node, then you can do insert. Okay. So that's why, because the condition for us to stop the search is you reach a null node. Okay. And then that means the cursor is null. Then you stop search. Okay. And at the same time, because you keep track of the parent node, is it? So now you can set a parent left or right to the new bin node. Okay, so that's the general idea. So we can take a look like insert 59 or 56. Okay. So then you compare with the root node. We always start. So it's greater than, so that means we need to do the right search. Okay, continue our search. So then compare with 65. So it's less than, so we need to go its left. And its left node is 57. So 56 is less than 57. So you should go to its left. And its left is basically a null node, is it? So if it's not, you stop. At the same time, we also keep track of the parent, is it? So let's come back again. Okay, we start at the root node, and now this is a cursor, is 55, is it? Parent is null. And then when it move to 65, so cursor will be 65, then parent will be at 55. Okay. Then you move to here, 57. So 57, then cursor is 57, and the parent is 65. Okay. And then you see it's compare, it's less than, so you say, okay, let's go to left, is it? So cursor is null, and the parent is 57. At this point, we stop. Okay, we stop, then you create a new node. So you can have a new node be created, like a new bin node that with 56. And now, no. Okay, you create this new node, and then you can set, in this case, the parents left equals this new node. So you let parents left doesn't point to null anymore. You let it point to this new node. Okay, yeah, that's how we do the insert. So we can also see for insert, it also involves the search operation at a certain point that you first need to find where to insert. And then, so with insertion, you also need to create a new bin node, okay? After you create the new bin node, then you connect this new node with the parents left or right. So that's how insert operation works in binary search tree. Okay, and then how do we do traversing? Okay, so how do we visit node by node? Is it, and also for the whole tree, the complete tree? How do we do that? Is it because this time it's not a linear structure? So how do we do that? Okay, and all of this, we are going to see there are three kind of approach, and it's recursive traversing. Okay, it involves recursively, and this is depth first search. Okay, so you go to one branch as deep as possible, basically. So we call it a depth first search traversal. So there are three different traversing order. The first we call it in order traversing. So in order, it's visit left subtree and then node and then right. So we call it in order, left node and right. Okay. Why we see this in order? Because we are going to see the output of this result will be completely in ascending order. That's the feature, okay? And the second is pre-order. Pre-order is node first, then left, and then right. So node, left, and right. So for this one, then root node visited first. Okay, because it's node. We start at root node, is it? And the last one, the third one is called post order. So left, right, and node. So left subtree, right subtree, and then node. So root will be lastly visited. Okay, so but anyway, in our example, we are also going to see, okay, so all three, the belong to depth first search, okay, and the implementation of our example, we are also going to see it's we implement recursively. So that's about the depth first traversing recursively, okay, to do depth first traversing. Okay, so let's see. We do in order. Okay, so in order is left node and right. Okay, so let's see how do we do the traversing steps first. So of course you always start at the root node, is it? But you are not going to stop because it's left. So you go to the left subtree. So the left subtree is this one, okay, you know the F's. And then you are not going to stop, you go to its left subtree. Okay, this is its left subtree. And with this left subtree, you go to left. So left, left nothing, and then node. Okay, node is B, okay. Then right, okay, right is C. Okay, we stop. So this left tree is done. We can cross it out, is it? So for node F, then it's left node and right. It doesn't have right, is it? So anyway, we are going to output F, okay? Okay, after this node, we are done with left node and right. We can cross out, okay? Then come to G, is it? Okay, for G, the left part is done, then the node itself, okay, it's G. Okay, so now this part is done. Then we move to its right subtree. Okay, for its right subtree, we still need to follow. We cannot start with J, okay? Start left first, so you go to left. Okay, this is left because it only has the node itself. Left is null, right is null. There's a left node and right. So that's why we go to I. So it's left is done. And then come to node itself. Okay, node J is done. And then come to its right. Okay, so that's the right. So right, and we should follow left, node, and right. Is it because left and right are null? Is it so left is null, so then come to node. And then go to right. Right is null. So now you are done with also its right subtree. So now this whole right subtree is done and everything crossed out. So this will be the output. As we can also see the output is in ascending order. So for binary search tree, okay, if you want the output, if you want to get ascending order output, you can pick this in order traversing. in order traversing. Okay, and the implementation is using recursive. Okay, but the idea is so similar with the pre-order and the post-order. So similar, but be careful. It's here left and right. It's not about the node. It's about the subtree. Okay, only when you done the complete subtree, then you move to the node. Okay, so just be careful about the left and right here's definitions regarding its whole subtree. Okay, only when you're done with the whole subtree, then you move to the node. So similar for pre-order and post-order. Okay. Okay, before we move to the next section, so let's take a look another national park. Okay, so this is the photo I took at the national park. So, and here is the other photo. Yeah. So can you guess which national park it is? Okay, so that's for this section, and we are going to come back a little bit later. Bye.